So now we're going to move into kind of the control and indication we see, and that was also more of our analog aircraft. Now we're going to look at control and indication of electrical with an ICAS-based aircraft. ICAS, when we do indication, when we discuss indication, it's Engine Indicating Crew Alerting System, basically electronic cockpit. And in this case, pretty much every aircraft that is ICAS that has a digital flight deck also has a split bus AC electrical system. And that's what's shown here. So we have, in a case like this, on the left is an ICAS display. And for the same aircraft on the right, we have a schematic that would come out of like a manual or training or other technical documentation. And if you look at them side by side, you can see they're very, very similar. Right? So, oops, got ahead of myself. So this is a twin engine airplane. We have two engines at the top. This one goes from top to bottom. Sometimes these are drawn from bottom to top, but this one happens Here we go. Test that again. I don't know how much of that we lost, but you should be able to get the video if you go to the link if you missed the circuit breaker thing. So there's the video link at the bottom. Okay. Circuit breakers are going to be arranged in panels as we've seen on the aircraft. Older aircraft into the 1990s, again, as I mentioned, had those buses located in the cockpit. Circuit breakers were all on the buses. But then as there was more concern about, fire and trying to eliminate that kind of thing, and danger, they moved the circuit breakers, especially the high current circuit breakers, down into the electrical and equipment bays. Okay, so older aircraft kind of look like that. There's what they call E&E bay in the cockpit or right under the cockpit. Everything's centralized and power gets sent out all over the aircraft. Okay, so power from the engines in this case was routed to the E&E bay, to the main buses. Originally they were above the floor. The main buses in the 727 are behind the flight engineer. Then they were moved under the floor, but they were still high current in one area. Your newest aircraft, rather than having just one main area, they're going to have distribution buses throughout the aircraft in several areas. So that way now, when you have, like they're showing here, when you have a load, or these are generators, these are the APU generators, but then you've got various loads in the tail, they kind of do the main bus switching in the wing box area, and then the forward E&E bay, that's going to power stuff in the cockpit, maybe the front galley lavatory area, and then stuff kind of in the middle of the airplane, in front of the wing, you're going to have another kind of bus area there to power loads in that area. So it's less running high current, right? Because if when the forward electrical and equipment bay was up near the nose here, you had big cables going from the engine up to the nose, and then say your hydraulic pumps are back in the wing box area, that's usually where they're located. Now you've got another big cable going from the nose back to the wing box. But if you take your high current from your engine generators to some boxes, you kind of do a distribution point in the wing box, that powers the big loads in the wing box. The E&E bay in the nose powers the big loads in the nose. The E&E back by the tail, that powers the bigger loads in the tail. And that way you're not running big high current wires everywhere. It makes it safer, right? You don't have as many places where those big cables could chafe or get damaged. And it makes the airplane lighter because you only run high current cables where they need to go rather than all over the place. And when you have longer runs of wire, you can stick with smaller wires that are lighter weight. The other part was the circuit breakers, going to almost all exclusively remote control circuit breakers, or RCCBs, which on your newest aircraft basically allow either control by control breakers in the cockpit that are all low current, half amp, 1 amp at the, maybe 2 amps at the most, versus 30, 40, 50 amps that you had before for main loads. And then your newest aircraft are controlled by ICAS and ECAM touchscreens and those kind of things, rather than even having any kind of a physical breaker. So the breaker panels look like this. You can see these are all those little plungers. They're all pretty much in the set position. There's a few here that this airline put these little collars on. Those are for breakers you want the crew to be able to find quickly. On most aircraft, for instance, the stab trim circuit breaker has one of these collars on it, if in case you have a stabilizer trim runaway, which can make the airplane unflyable. It's a little 737 MAX thing, but even before that. So those often have a collar where if they're having a stab trim runaway, they can quickly identify and pull that breaker to disable the stabilizer trim. So it doesn't nose the airplane down into a permanent dive or nose it up into a permanent stall. But your newest aircraft, here's an example of a ICAS system that has the circuit breaker control on it, with the actual circuit breakers being remote control circuit breakers that would be down in an electrical bay somewhere. And so you have different breakers. You can see, like here it says, in the middle one here, we've got fan, miscellaneous, and they put a little do not close. The maintenance can go in and actually lock them in a open position with a virtual collar. That's what it's showing there, is it's got a virtual collar, like those little clips you see on some of the breakers in the 727. You can put a virtual collar on it. And then maintenance, you have to go into the maintenance area in order to put those on, and you have to go into the maintenance area of the ICAS system to take them off. You can see just below that, supply fan, FD equipment, can't remember what that is. There's a green breaker pushed in. A little further down, supply fan forward equipment is white. That means it's pulled out right there. Okay. And then further down, about most of the way to the bottom, outboard forward equipment, cooling, you can see a tripped breaker, where it actually goes in like a yellow-orange with the trip word next to it. So you can pull a breaker, that's the white one, or you can have a breaker in a trip position. And then if there's a failure of the remote control circuit breaker, you can see some of them have an unknown thing. They also have the circuit breaker numbers over here on the left, the names. You can get data from them, which can include things like this one is pulled, it says, or open. You know, it can tell you what the rating is. Output status is off because it's open. You know, and then there's a control page. You hit the control page, and this is where you can close it, lock it, or cancel to exit out of the page. So, and this is a touch screen. So it's a pretty slick way of doing it, where you no longer have these big, heavy panels up in the cockpit. And there's enough redundancy built into the ICAS system and the computers that control this and the number of screens that you can use, you can use this instead of having a physical version like this. So that wraps up AC. Getting into DC, we're going to start with our sources. So DC starts with a transformer rectifier unit. This is going to take AC power, which is an input power, 3-phase, 120 volt, 400 hertz AC, and it's going to convert it to DC. And that's our primary power. When the airplane's up and running in a ground power unit situation, an APU generator situation, an engine generator situation, this is how the DC system is going to get power. You know, the ground power unit, the AC generators on the engines, the AC generators on the APU are going to power the AC system. The AC system is going to power the transformer rectifiers or transformer rectifier units. It's it's the same thing, just different manufacturers will call them the two. You know, one will call it, it'll have the unit on the end. So TRU or TR, pretty common acronym for it in aviation. That's going to take AC converted to DC. As a backup, also before we have AC power available, we'll have batteries of some sort on board. NiCad, lead acid, and now even some aircraft have lithium ion. And there's other lithium, you know, some of these newer batteries that are coming out that they're investigating being able to use, mainly because of the weight savings. Some of these new lithium batteries, lithium formulation batteries coming out are significantly lighter than, say, a lead acid battery. And then the third one is ground power. There's typically a way to hook up ground power. Not all transport aircraft have a DC ground power hookup, though. Some of the aircraft I worked on did not have a way to hook up a DC ground power source. Because the assumption is if you're hooking up ground power, it's probably going to be AC. It's very rare you need a just DC. And if you can hook up AC power, it's going to power the DC system. And if you hook up AC power and it's not working, you're probably not too worried about the DC system working because you're going to have to get the AC system working before you can do anything anyways. So they've actually eliminated DC ground power on some aircraft. Still has a DC system, just no way to hook up a 24 volt cart, 28 volt cart. So here's what a TRU, some different examples they look like. So it takes that 120 volt, converts it to 28 volts DC, feeds the DC buses. It works a lot like a battery charger. It's basically like a battery charger that would run stuff. And in fact, one of the, let's see, I worked on an aircraft that had these right here. The TRUs and the battery chargers were identical. It's just when you hooked up this little plug, so this is your main power out right here. J1 had, you know, there was 3-phase in, And then there were some control things, and there were some jumpers you could set on it. You could set a little jumper as it was a TRU, or you could move that jumper over and it would work like a battery charger. So you could actually move them into different locations if you needed to. If we had a plane where one of these failed out at an outstation, the one that charged the batteries for emergency use had to work to fly the airplane, right? You always want your batteries charged in case of an emergency. The non-essential DC bus TRU, you could defer for like 10 days. It didn't have to work for 10 days. It could get power from somewhere else. So if you were somewhere where your backup, your emergency battery charger went bad, you could actually swap that with the good one from another location and get the airplane flying again. You put it in so that's why they do it that way, is now instead of having to have a DC TRU or a TRU on the shelf as well as a battery charger on the shelf, we just have one box sitting on the shelf that can go anywhere. So each TRU powers one or more buses, and then could be a battery charger. And then the batteries themselves I talked about could be various, there's different, lead acid, NiCad, lithium ion. And lead acid is still very, very common. We actually had lead acid on one airplane. We switched them all to NiCad, and then they realized the maintenance was more expensive. We switched them because they were lighter weight and they were supposed to last longer. But when they worked out the maintenance costs, there's a little more maintenance and stuff on the NiCads. We just went back to the lead acids, would run them until they die and put a new one in. It was cheaper to do that than to buy the more expensive lead acids, or more expensive NiCads and have to maintain them. And then on the ground, these are used for APU starting and system startup. They got to get the airplane going. You can't store AC, so we use DC as a self-contained storage device. In the air, they're a backup, or in some cases even considered an emergency power source if you lose all other power. The buses and circuit breakers in DC are identical to AC, so I'm not going to re-discuss them. Basically, go back and look at the AC section. They work the same way. Your power sources, your DC power sources, power the DC buses. The DC buses have circuit breakers on them that distribute power out to the various loads. Okay. Or to secondary buses like the service bus or the non-essential bus. So control for these, oftentimes there are switches. You can see in this panel, they can be auto or off. Typically you would leave them in auto. Powers a TRU here. So this shows, you can see on this aircraft, we've got our AC power is this top area. And then we've got AC bus 1 coming down, powering TRU1. We have AC bus 2 powering TRU2. TRU1 powers DC bus 1. TRU2 powers DC bus 2. You can see the DC, you can see that changeover. Here's this line right here in the middle, AC above it, DC below. That's kind of the switchover point, and the TRU is where that takes place. Really, if this was drawn perfectly accurate, the TRU would be right on that line, right? Because AC would come in the top and DC out the bottom. But, we've got an essential TRU essential for DC, which comes off the AC essential bus, which can be powered from either AC bus. And that powers the DC essential bus down here. There's the switch for the essential bus, the switch for the TRU2. Here are the switches for the hot battery bus. Okay, be able to connect, turn the battery on. So we've got battery 1 right here. Powers a hot battery bus. You can see battery 1 is connected to a bus that has no switches, no contactors or anything. Okay. The hot battery bus can also often serve as an emergency bus. That's why when we power up the 727, we plug in the battery and we go up in the cockpit and there's a few lights on in there, a few indications. One of those is the stall warning system. It can run off DC battery. If the battery's plugged in, the stall warning system is working. Because it's that critical to the airplane to maintain, whether that airplane's flying or gliding, you want to know if it's stalling or not. You want to make sure it's not stalling. So that's hooked to the hot battery bus, for instance. There's DC bus 2, essential bus 2. Okay. So that serves as an emergency. That's off of another hot battery bus here from battery 2. Okay. APU start bus down here is to power the AC. So battery 2 in this case powers the APU starting. This airplane can take a DC ground power source, mainly for APU starting, if for some reason the APU battery's dead. You can see various contactors controlled by switches. So control is pretty much the same as what we have with our AC systems. Let's go ahead and we'll stop here. We'll take a break and we'll get into electrical generation when we come back from a 10-minute break.